Okay, guys. So we have been spending the last couple of class periods doing the investigation, looking at milk under a microscope, watching in that petri dish how the vinegar as a gas was actually reacting with the bromothionyl blue and was causing a reaction to happen. So gas was making the movement. That was the invisible ghost. We looked at the beakers of water, cold water. The food coloring didn't want to move throughout the beaker. Whereas it was warmer, it was filling that beaker with red much quicker because as temperature goes up, particle movement goes up as well. So all of that is dealing with this idea of the kinetic molecular theory. So today, what I want to do is walk you through some of the notes with this. Remember, at any point you can push pause, but this is your BP packet, BP1 packet, and we're going to fill in this front page. So we began with investigation, asking questions, and now we're going to try to piece together some of that stuff that we've learned. And I want to start by just showing you a video. You know, there's this word that's in front of a lot of our milk cartons called homogenized and what that means. But the fact that it is homogenized milk let you see the little fat droplets shake back and forth like it did. And really what we need to get at is, you know, they were shaking back and forth because water molecules we couldn't even see were hitting those really big fat droplets from all directions. It was hitting it. All right. So I'm going to go ahead and push play and we'll watch this video and then we'll come back whenever it's done.
Cream off the top and shake up the milk. Times have certainly changed because most of the milk we drink today is both pasteurized and homogenized. But now I'm wondering, what's the difference between the two and what exactly do they do? We pour a glass of milk and drink it, but do we ever think about what's in it? In simplest terms, milk is a combination of milk fat globules and water. In its raw form, if not shaken, the cream settles to the top. But today we don't have to shake our milk anymore because of a process called homogenization. In 1899, August Gallin patented the first homogenizer. When milk is homogenized, the fat globules are shattered under a lot of pressure, so they stay immersed in the milk. The higher the pressure, the smaller the particles. Now, pasteurization is a completely different story. In 1864, a man by the name of Louis Pasteur invented pasteurization to reduce the number of harmful pathogens in milk and extend its shelf life. So next time you drink a glass of milk, think about the wonders of pasteurization and homogenization. Under Louisiana law, all milk sold for consumption must be pasteurized but does not have to be homogenized. Now moving on to this week's Twilight Trivia. Last week I asked you, how old is the average heifer when she first calves? And the correct answer is...
So a little bit of fun, you know, whenever we get milk now, it is definitely homogenized. It looks the same throughout. And that's what allows us to see those fat globules. And that movement actually has a name. It's called Brownian motion that we're watching. You could see this, like if you were to look, especially in your window, the sun rays maybe comes in through a room and you've seen like little dust particles and they look like they're dancing around. Pay attention next time. Try to pinpoint one dust particle, watch it, and it's going to move about like that same weird movement that we saw the milk particles do. And what's happening is you have other air molecules that are even smaller than the dust that are hitting it from all directions, three-dimensionally, and it's making that dust particle dance around and do really, really weird things. So all of that's Brownian motion. What we're going to do, ooh, that's kind of hard. Let me turn off a set of lights. That's a little rough to see with the color that I picked. Okay, there we go. So let's get our note packet out and let's fill in some of these terms. So one of the things is, you know, kinetic. When we think kinetic, you have to think movement or motion. So we need to have that knowledge base. Whenever we think kinetic energy, we're thinking the energy of motion. So all things that are moving have kinetic energy. You have kinetic energy because there's things inside of you that are moving. Weird to think about, right? You have even more kinetic energy when you actually start to walk. But even at the particle level, there's kinetic energy of those things inside of you. Kinetic theory is a theory that explains the motion of all the particles or atoms and how they move at an atomic level. Okay, so it explains that motion. So whenever we look, and I used to have folks write out all the parts of the kinetic theory. There's really 4 different parts, but I've kind of smushed it into one big statement, what I think is most important right now for us to take away with this unit. And this is what I'd like for you to write. Remember, at any point, you can push pause and do a little bit more detailed information, write it down, get it down before we move on. So all matter, meaning atoms and molecules, are in constant straight line motion. As they heat up, they move faster. And we saw that with that beaker of water. So just catch that. Go ahead and write that down. And I want to show you, I still have the beakers. So as you would expect, now over time, look, it's completely filled the beakers. Why? Because they're all room temperature. Eventually it will fill the beakers, but as temperature was higher, it filled the beakers quicker because the motion was faster as well. So even the food coloring particles were moving through faster because it was warmer. All right, so how does kinetic energy apply to temperature? What's that connection? Well, temperature is the measurement of the average kinetic energy of a sample. So whatever it is we're taking temperature of, it's a measurement of how fast it's moving. The higher the number, the faster those particles are moving. So when we took the temperature of the warmer water compared to the cold water, that's our indication. Those particles are moving faster in the warm water than they are in the cold water. Okay, so literally kinetic energy and temperature is telling us how fast those particles are moving. Heating up a substance is going to raise its kinetic energy. It's going to make it move faster. We saw that impact. And then there's this strange number that's given to temperature that's called absolute zero. And we're going to watch a little video here in a second about it. But absolute zero is quantitatively, so numerically, it's described as negative 273 degrees Celsius. That's really, really cold. If we were to look at that in Fahrenheit, that's negative 460 degrees Fahrenheit. So crazy cold. We're never going to reach that on the planet Earth, I hope. The closest they've gotten, and you're going to see in this video, is in outer space where it's already cold, so you're not having outside temperatures trying to increase. We also give this a third measurement unit, and it's called Kelvin. So 0K or 0 Kelvin. So all of those things numerically mean the same thing. They mean absolute zero. What is that defined as? Well, it's the temperature at which supposedly all motion stops. Okay, we've never gotten exactly down to absolute zero, but we've gotten really, really close. You got to remember, scientists are very detail oriented, and you're going to see in this video how close they've gotten. And a lot of us might go, well, geez, now come on, isn't that really we've gotten there? But a scientist would say, no, it's not ever good enough that we can get closer and closer to absolute zero. So let's take a second to actually watch this video, and then we'll come back and talk a little bit about it. But this is just more like a factoid video that helps you see what absolute zero is.
Part of the International Space Station is about to get very cold, like colder than any place in the known universe cold. And we don't really know what's going to happen when it does, but we're doing it on purpose. Creating an environment that's as cold as the laws of physics will allow is the holy grail of quantum mechanics. That's because the less heat that something has, the less energy its atoms have to move around. So at some point, you'd think that it could get cold enough that they'd stop moving entirely. We call that point absolute zero. But it's only theoretical. Nothing can ever get that cold. Just like we can't get to the speed of light because we need an infinite amount of work, we can't cool anything to absolute zero because we need to extract an infinite amount of heat. But we can get pretty close. And when the Cold Atom Laboratory launches to the International Space Station in 2016, we'll get closer than ever. When the lab starts working, it will become the coldest place in the known universe. Now, space itself is really, really cold, with an average temperature of 2.7 Kelvin. And the coldest natural place that scientists know of is the Boomerang Nebula, which is 1 Kelvin. So for now, the coldest places in the universe are actually on Earth. in labs around the globe that can cool collections of atoms to within a few nanokelvin or billionths of a degree of absolute zero. But the cold atom lab will be capable of cooling gases down even more to just 1 picokelvin. That's only a trillionth of a degree above absolute zero. But other than the fact that this experiment would be literally cooler than cool, why bother doing it? Because when matter gets even closer to absolute zero, it can take on all kinds of new properties that are as crazy as they are useful. And it's all because of changes that take place at the tiny, mind-blowing quantum level. All particles of matter occupy what's known as a quantum state, which describes statistically how they behave based on their energy. Most of the time, different particles will occupy all kinds of different quantum states because they all have different amounts of energy. But when you get really close to absolute zero, like within a few nanokelvin, atoms have so little energy that those differences begin to disappear. Instead, atoms become incredibly orderly, and most of them will enter the lowest quantum state. When that happens, they can end up forming substances with properties like superfluidity, where matter looks like it's propelling itself all over the place with no regard for gravity, and superconductivity, where matter becomes a perfect conductor of electricity with no resistance. These properties have all sorts of potential applications, like in quantum computing, for example, a type of super-fast quantum-based information processing that's probably the future of computers. So naturally, physicists are interested in figuring out how to get things as cold as possible to create these awesome properties. But one of the main problems is, on Earth, they're limited because of gravity. No matter how cold, calm, and orderly you try to make atoms on Earth, gravity is always there, constantly trying to pull atoms away and mess up your sample. But the cold atom lab won't have that problem. The lab will use cooling techniques that are similar to those on Earth, trapping particles of gas using lasers and magnetic fields. But since it will be in microgravity, the lab won't have to support the matter against the pull of Earth's gravity. This will not only make it easier to get matter into the lowest possible quantum state, it also buys scientists a lot more time to study it. On Earth, you're lucky if you can keep atoms in place for more than 25 milliseconds. But in space, they'll have up to 20 whole seconds at a time to see how matter behaves near absolute zero. The truth is, when they do manage to cool atoms down to a picokelvin or two, no one really knows for sure what's going to happen. Researchers could discover quantum phenomena that no one's ever seen before, or maybe even entirely new kinds of matter. Guess we'll just have to wait and see. But you can trust that you'll hear it from us first. Thanks for joining me for SciShow Space. If you want to keep exploring the universe with us, then just go to patreon.com/scishow to learn how you can become a space patron.
Okay, so that gives you just a little bit of background with absolute zero. And your big takeaway is no, that's a temperature when theoretically all motion is supposed to stop. I know I've seen a couple sci-fi movies that deal with that. A couple of them are pretty good. Okay, so how does the kinetic molecular theory give rise to the different states of matter? Well, as temperature, I'm going to do my other solar lights. As temperature increases, there's a few things that happen. First of all, particles are going to move faster. Okay, particles will move faster. They will increase their kinetic energy. Remember, you can hit pause at any point. And that will cause them to change from a solid to a liquid to a gas. Okay, so that's the basic idea. So whenever we break these apart and we get a little more detailed about these different states of matter, and we think of them from the solid point of view, and then we're going to go through the liquid point and then again the gaseous point, we have to keep thinking, again, how does that kinetic molecular theory give rise to all three? So this is a final video that I want you to watch that'll help us see those things.
The kinetic molecular theory is the theory that all matter is made up of atoms and molecules that are always moving. These particles hold kinetic energy and move around in random directions. In higher temperatures, the particles have high energy, and in low temperatures, the particles have less energy. The more energy a particle has, the faster it will move. In solids such as ice, the particles hardly move at all and hold a regular pattern because the energy is low and the particles are tightly packed. In liquids such as water, the particles have more energy and the freedom to move around. Liquids have the ability to flow and fill the shape of any container they are put in. In gases like steam, the particles have the most energy. These particles are sparse and move around freely. Gases are usually invisible to the eye and they can be expanded and compressed in different pressures. All matter is composed of atoms and molecules that are always moving. The higher the temperature, the more energy these particles have. And that is the kinetic molecular theory.
Okay, so a little bit of a funny video to talk about how it would give rise to those different things. So if we look in the solid state and just some characteristics of that. So solid particles are going to vibrate in a fixed point. They are connected. So here's an example of like a crystal solid particle. So each atom is connected to another atom and they will move, but not very well because there's these bonds in between. Okay, they have what's called really strong intermolecular bonds between one atom and another. So they'll sit there and they'll shake in place, but they don't get to freely move past. You know, this atom right here doesn't get to waltz over down here and do something different. So they're in a fixed point, they're packaged in a highly organized pattern, and they tend to be very dense. The atoms inside a solid are close enough to interact very strongly with one another, and that's what I was saying. This is something that's called intermolecular forces. So inter means between molecules. So between molecule forces, very, very strong. So that gives us a beginning thought with solids. We're going to get into this a little bit more as time goes on. If we were to look at liquids, so liquid particles have more kinetic energy than solids. What does kinetic energy mean? Moving energy. So if this solid were to become a liquid, now this atom right here could actually leave, it could disengage, and it might flow down here. They'll still flow around each other. They're still interacting with each other, but they can move into different spots, okay? And even think, you know, if you ever got to watch sugar melt, you can put sugar in a pan, put it right on the stove, and it'll melt. If you do that, make sure your parents are okay with it. And it changes its shape. It all of a sudden seems like it's flowing because these atoms are allowed to move more freely around each other. They do exhibit intermolecular forces, not as strong as solids would, but they do exhibit those. And they have particles that are less closely associated with each other. They can move around each other. Okay, so they're less closely associated with each other than solids are, but they're more closely associated with each other than gases. Okay, in order for a liquid to become a gas, there needs to be enough kinetic energy to overcome those intermolecular forces of them liking each other. And we're going to do this in a little bit, not today, but a different day with a warm up using some water molecules. Then if we look at gases, so gases are made up of a few particles, just a couple of particles. Now imagine, again, going from a solid, now we take this apart, we turn into a gas, and there's just a few. So here's one gas particle, here's another one. There's very few in a given space because there is a bunch of empty space in there. So you got one particle over here, you got one over here, and you have tons of empty space in between. Because the atoms and compounds are so far apart in that state of matter of a gas, there's really no attraction to each other. So this one shows no attraction to this particle over here. There's no repulsion. What that means is there's no intermolecular forces with those, okay? So that kind of sums up the notes I want you to do for now. The next time that you're here with me, you're going to be doing an investigation regarding water and the three states of matter that it can exist in. So as ice, liquid, and then as steam, a gas. You're going to get to make your own lab investigation. Tell me what you come up with as some ideas. Make sure it's parent approved. And then we will discuss your results. So we're done for now. I hope you guys are having a great day and get outside as much as you can, even if it's raining. Rain never made any of us melt, right? All right, we'll see you later.